In this video, we'll be checking out on modules, left modules and right arrow modules. So in modules, in most cases in this video, what we'll be deliberating on is just left arrow module. But before that, module simply means the generalization of vector space. Now, but in this case, we are not considering the scalars to be from a field. Rather, we are taking the scalars to be from an arbitrary ring. Do you understand? So the scalars are from arbitrary ring. Now, the general definition of modules, it is that let R be any ring that is, of course, it must be non-empty set M. So it is said to be left or right regardless. It is said to be left or right because we are defining the full definition of a module. We are less concerned if it is a left R module or a right R module. So if you are asked to define a module, you have to define it regardless of it being a right R module or a left R module. But if it is indicated that you should define a left R module or you should define a right R module, so you should also note that. So if the following condition holds, that is M plus is abelian, so there is a defined scalar multiplication for R in R and M in M. Now the defined scalar multiplication is actually from a ring and not from a field. So that is it for the definition of a module. Now a left R module, let R be a ring with identity. Now it is not necessarily commutative. Why? Because we are defining a left R module, so commutativity is not essential. So a left R module over R, we can also call it a left R module over R, is an abelian group. Now one amazing thing about both left R module and right R module is that they are both abelian group together with a scalar multiplication, and they must satisfy the following axioms. So you can see the axioms there. Now for a right R module, the right R module, you can see left R module is represented as Rm. Do you understand? So the right R module is it's kind of the opposite of left R module, and you can see the axioms as follow: M1 plus M2 R. So in right R modules, what matters is the arrangement. You can see from the first one we have R dot, and the second one we have dot R. So that is just the difference between a right R module and a left R module. So it is the arrangement that matters. So you can take note of the definition. Now, one important proof that you can never escape when it comes to the modules generally, is that every abelian group G is an R module over the ring of integers. So what we usually do is to apply all the laws of modules. Now let G be an abelian group, and of course there's a define. If it is an abelian group, one automatic thing that happens is that there is a defined scalar multiplication for G in G, N in G, and for every value of Ng in G. Now what this simply means is that Ng, it's simply the mapping from G and Z. I should have written that Ng is simply the mapping from G and Z. You understand? So when we pick 2G in G and we add them together, when we pick 3G in G and we add them together, and when we pick N1, that is axiom 1. Now this is axiom 2. Now N1 plus N2 times G, so that is the axioms. And lastly, N1 times N2 times G. So you can see this follows the axioms of a module, regardless of it being right or left. But in most cases, what we usually do in most of the proving is we use the left R module in most of the proving. You understand? Now we have a lemma. We have that let M be an R module and X is in M. So the O, or the zero is in R times X. 0 times X will give us 0. But this 0 is in R, and as well we also have another 0 when it is coming, when the scalar multiplication is multiplied with 0, the 0 is now in M. Do you understand? So similarly, any abelian group over the ring of integer, that is a module, that is a Z module. We call it any abelian group over the ring of integer is a Z module, and we can also prove that. Okay, now this implies that M plus is abelian. Of course, that word is very important. M plus is abelian. Therefore, there is this Z in R that is mapped to M. Since it is abelian, of course it will be mapped to N, and that's NX as well will also be mapped to NX, where N is in Z and X is in M. So now following the axioms now from the lemma that we have above, when we pick 0, oh, let's start from 1 times x, that's x. And when we pick 0, we can have it as 0 plus 0x. And of course, the 0, you must indicate where the 0 lies. Do you understand? So that is that. Now, cases that the right R module is equals, when R is equals to M, sorry, when you should note that R is equals to M from Z map R to M. Do you understand? So that is it. So the next phase, we have that all non-zero scalars have multiplicative inverse. Of course, they have multiplicative inverse. That's, you can see from this axiom, we have that minus Rx equals to minus Rx, and that is equals to R minus X. Okay. So now there are some important things that you should be able to prove, or you should prove, and in the next video I'll be dropping this proof as well. Is any ring itself is an R module. Any ring itself is an R module. That is, when R equals to M, it simply means that a ring in itself will be represented as R subscript of R. You understand? So that is it. So any ring itself is an R module. Now the set of real numbers are also R modules. The set of real numbers are also R modules. The set of M times N matrices is an R module too. The set of M times N matrices, and the set of all polynomials is also an R module. Now let's show this example. We have to show that if M is a vector space F, then M is a module over F. That is F module. We have to prove F module in this case. So we write our mapping out, then we apply the axiom. What this simply means is that what we are doing in this case now is just to apply the laws of modules here, right left arrow modules. But in this case, we are saying that M is a vector space. M is regarded as a vector space in this case. So the only thing that will change is that all values of A are in the vector space, that is, they are in F. So you can see everything written here are still the axioms of what that. So if you are asked to show that M is a vector space, what they ask you to do is just to write out the axioms. Now, so recall that a vector space is defined axiomatically as an abelian group together with a product A M in M, for A in F, M in F, such that those conditions hold. So there's nothing changes when you are asked to prove the show that M is a vector space. What you need to do over a module F is just to write out the axiom and write out the recall. Now in the next video I'll be dropping the proof of a ring being itself is a ring in itself is an R module. The set of real numbers is an R module. The set of M times N matrices is an R module, and the set of all polynomials is an R module. So these are the basic things for class 1 on modules. Thank you.